So in this part, we are going to look at how to add binary as well as subtract binary. So here are a couple of things I'm going to do. So in this particular case, first of all, we need to learn the basics, right? So when it comes to binary additions, we know that when you add 0 and 0, right, then it will be 0. If we add 0 and 1, then it will be 1. When you add 1 and 0, it will be 1. If you have add 1 and 1, then 1 and 1, 2, meaning like this is 0, right? And 1 carried forward, so that means it will be 1, 0, right? So we know this is 1, this is 1, 2 in binaries, 1, 0. So this is the basic. So let's start with 1, 0, 1, 0. You add 1, 0, 0. Can you tell me the answer for this one? Yes, what is the answer for this one?
0, 1,
Yes,
1,
this one is 0,
1,
1,
1,
1, again 1 here, right? So 1, 0, 1, 0 means, if you know the positional values, this is 8, 4, 2, 1. So which means this is 10, right? And this is 4, right? So we are getting 40, right? So that means 8 plus 4, 12 plus 2, that is 40, right? So this is the answer. So likewise, if you add this one, can you tell me the answer?
0, 1, and 1.
Yes, this is 1 and 1, this will be 0. 1 will carry forward. So that means this becomes 1, this becomes 1. It's 1, 1, 0. If you check the answer, this is 5 and this is 1, that will get 6 here. Last one.
0,
Yeah, this will
0,
be 0. There will be 1 carry forward.
0,
Again, there will be 0, 2, then 1 carry forward.
0, 1.
Again, 0 and 1, right? So we have 1, 0, 0, 0. So this is 5. 4 plus 1 is 5. This is 3, right? 5 plus 3 is 8. So this is the answer. So we are getting the correct answer. Similarly, subtraction, right? So how subtraction works, let's look at with these two examples. If you subtract 0 from 1, we know answer is 1. If you subtract 1 from 1, the answer is, yes, 0. And then this will be 1. Okay. You can double check the answer. This is 7 and this is 2. 7 minus 2 means 5. So that's why we get 1, 0, 1. Yes, Dulina, can you perform this? Can you tell me the answer?
1,
Yeah, this is 1 because this is 0. So you take 1 from here and it becomes 2. 2 minus 1, this is 1. And then here we have 0. So 0 minus 0 is 0. Again, then you don't have 1. So you will take this here. So this becomes 2. 2 minus 1 is 1. And this will be 0. So this 1, 0, 1, 0 means 10. Minus 5 is 5. So that's why we'll get 1, 0, 1. Okay, let's take down this. So let's move to the next one then. The next one, we are going to look at how to measure the data, right? Data measurements. So we know that in computer, everything represented in binary, right? Um, Power is on and off, or we can say voltage high, low. Mathematically, we can represent 0 and 1. The amount of space you need in the computer to represent this 0 and 1 is known as bit. Now, bit stand for binary digit, right? Binary digit or bit, we call it. So, bit is the space you need to store either 0 and 1, right? Then this is how the unit works. If you take 8 bits together, we call 1 byte. And when you take 1024 bytes together, we call 1 kilobyte. 1024 kilobyte will take 1 megabyte. 1024 megabyte will take 1 gigabyte. 1024 gigabyte, we have 1 terabyte. 1024 terabyte, 1 petabyte, and so on. So you see that it's always multiplication of 1024 to get to the next level, right? So this 1024 is actually 2 to the power 10. Remember this one when we work on calculations, this is important. So it's not really, you know, 1024 is 2 to the power 10. So approximately sometimes when we perform calculation, we can take it as 1,000, right? I'll come to those when we discuss the questions. Okay, another thing you need to remember is a nibble is a half of a byte we call 4 bits, right? So these are the units that we will use for measurement. So let's do a couple of exercises. Now let's say we have given 3 into 2 to the power 20 bytes of the data. Now we are asked to convert this to bits, kilobytes, and megabytes. So let's start. So what we have is 3 into 2 to the power 20. We have bytes. We have 2 to the power 20 bytes. So how do you convert into bits? What do you have to do?
Divide by 8.
Yes, 1 byte is how many bits?
8 bits.
8 bits. 100 byte, how many bits?
80. 800.
800, right? So what do? You have to multiply by 8, isn't it? So that means 3 into 2 to the power 20 into a bytes. A 1 byte is 8 bits. So you have to multiply by 8 bits. So when you want to simplify, you can use put 8 as 2 to the power 3, because this is not easy to get the solution. So this is 2 to the power 3. That means we can say 3 into 2 to the power 23. So the next one, what we want to do, we have 3 into 2 to the power 20. We have bytes. And we want to calculate this in kilobytes, right? Kilobytes. So we know 1024 bytes equals to 1 kilobyte. So what is 1 byte then? 1 byte is equal to, yes, you have to divide both sides by 1024, isn't it? What do you mean by that? That means if you want to convert byte to kilobyte, basically you can divide by 1024. So that means 3 into 2 to the power 20, and you divide this by 1024 to get kilobytes. So you have to divide it. Again, 1024 bytes equal to 1 byte. So 1 byte is, then you have to divide kilobyte by 1024. So right now we have given in, bytes. So to replace byte, we can divide the bytes by 1024. So when you want to simplify, 3 to the power 2 to the power 20 divide by 2 to the power 10. That means this is division, meaning like you can subtract this. So that means 3 into 2 to the power 10 kilobyte. Now let's look at the next one. Again, we have 3 into 2 to the power 20 bytes, right? We know 1024 bytes equal to 1 kilobyte. Then 1024 kilobytes, 1 megabytes. Since 1 kilobyte is 1024 bytes, we know this is 1024. Kilobyte is 1024 bytes, so this will be 1024 into 1024 bytes, 1 megabyte. So if you need 1 byte, so 1 byte is equal to, let me erase this, right? So 1 byte, to get 1 byte, you have to divide both sides by 1024 into 1024. Right. Now we can finish. 3 to the power 2 to the power 3 by 2 to the power 20 bytes. We know that this is equal to 3 to the power 2 to the power 20. And if you divide this by 1024 into 1024, we'll get megabytes. So 1024 means 2 to the power 10. This is 2 to the power 10. So that means 3 into 2 to the power 20 divided by 2 to the power 20. So that means 3 megabytes. 3 megabytes. So here we are going to discuss the storage requirements for different things. And this is approximate, not 100% correct, but for the approximate values, we can put it, right? So when you start, you will see that how many bits you need to represent right and wrong answer, right? That means you have two choices. So we can represent using either 0 and 1, right? Let's say 0, wrong, then 1. So that means you need one bit of information. One bit is enough. Then let's look at how to represent numbers from 0 to 255. We know one thing, one bit can be used to represent two numbers. Yes, what is this? 0 and 1. So that means the values that you can represent is 0 to 1. If you have two bits, then you can represent four numbers. What are the four numbers? 0, 0, 0, 1, 1, 0, 1, 1. That means the values goes from 0 to 3, isn't it? You can represent four numbers. So likewise, if you represent 3 bits, yes, if you have 3 bits, then the values will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So basically, you see the numbers, you can represent 8 numbers from 0 to 7. Right? The question asks, how many bits you need to represent numbers from 0 to 255? Yes, calculate it and see. So in 1 bit, it goes from 0 to 1. 2 numbers. 2 bits, it goes from 0 to 3. So that is 4 numbers. You can see 2 to the power 2, right? If you have 3 bits, 2 to the power 3 is 8. The values go from 0 to 7. So likewise, if you calculate, if you have 4 bits, then you have 16. The values go from 0 to 15. If the number is 5, then value is 32. 2 to the power 5 is 32. The values go from 0 to 31. So likewise, if you start with 6, then you will get 64. The values grow from 0 to 63. 7, you have 128. Values go from 0 to 1 to 7. 8, it's 256. That means values go from 0 to 255. So that means you need 8 bits. In other words, you can say it's 1 byte. And if I put roughly, we will discuss this later on. If you take a single line in a book, assuming that one character is 1 byte, usually we need about 90 bytes. And for example, if you take a page, at least something around like 4 kilobytes, this is approximate value. If you take image, approximately you can say 1 megabyte. Depend on the quality, this number is also vary. 3 minutes so like MP3, you need approximately about 3 megabytes. Capacity in different storage media like a hard disk, if you're going to purchase nowadays, we have about 1 terabyte. Yes. Floppy disk is old one. It had around like 1.44 megabytes. Flash drives, maybe 8 gigabytes. Memory sticks, maybe 4 gigabytes. CD-ROM is fixed, 700 megabytes. And DVD, it's about 4.7 gigabytes. And Blu-ray, roughly about 25 gigabytes. This is how different storage will work and their capacities. Two simple questions given. I want you to try at home. So please, you can take down the note. It asks how many CDs are needed to store information in a DVD, right? So what we know right now is the amount of information you can have a DVD is 4.7 gigabytes, right? So that's a DVD. And CD, you have about 700 megabytes. Now to find out how many CDs you need to store information in a DVD, right? So the number of CDs equals to, we have 4.7 gigabytes divided by 700 megabytes. So you have to divide this, right? 4.7 with 700. Okay. Yes, can you try and let me know? So to divide 4.7 gigabytes into 700 megabytes. So this is, you have to multiply by 1024 and divide 700. You will get about approximately 6.8 CDs. So we have to round it off. So that means you need 7 CDs. Right. The next thing that we have discussed, right, the digital image size is 1 megabyte. And the CD can have the data about 700 megabytes. Right? So how many digital images you can store?
700.
7, right? Okay. Right. Next one is some homework, but I'll copy. So far we have learned how to store numbers, right? And then we also discuss how to put numbers into binary, octal, hexadecimal, and so on. But how about the other things like characters and so on? So for that, we will use coding system. So coding system is actually used to represent different characters, even the numbers and control keys. So under this, we are going to discuss a couple of coding systems. So let's start with the first one. It's known as BCD, or binary coded decimal. So in this particular case, when you say BCD, right? So each number is represented using 4 bits. So remember this, we are using 4 bits. But each number, right? The numbers goes from 0 to 9. So that means you need only 10, digits. But when you have 4 bits, you also know that you can represent 16 values. So let's see how this will work, right? So as I told you earlier, binary coded decimal means We are going to represent each of these decimal numbers using 4-bit binary number. So the decimal numbers we know, we have 0, we have 1, we have 2, we have 3, we have 4, 5, 6, 7, 8, and we have 9, right? So when it comes to BCD, so it will be 0, 0, 0, 0, right? Then we have 0, 0, 0, 1. We have 0, 0, 1, 0. Then we have 0, 0, 1, 1. That is 3. Then we have 0, 1, 0, 0. We have 0, 1, 0, 1. Then 0, 1, 1, 0. Then 0, 1, 1, 1. Then 1, 0, 0, 0. Then 1, 0, 0, 1. Right? So the values after this, that means 1, 0, 1, 0, 1, 0, 1, 1, 0, 0. So these are not valid BC numbers, right? So the remaining ones. So what are the remaining ones? That means after 1, 0, 1, 0, right? Then 1, 0, 1, 1. Then 1, 1, 0, 0. Then 1, 1, 0, 1. Then 1, 1, 1, 0. Finally 1, 1, 1, 1. All these are not valid, right? Not valid, right? So these are not valid BCD numbers. Make a note of that. Very important. These are not valid BC numbers. Now, for example, when you say 10, let's say you want to represent 10. 10. So how do you represent 10? Yes. So there's no something called 1010. So what you have to do is we have to represent 1. So how do you represent 1? We have 0, 0, 0, 1, and then 0, 0, 0, 0, 0. So this is how we will represent 10, not like this, right? So remember this, very, very important. So 1010 to 1111 are not valid BC numbers. So when you say 10, you represent 1 separately, then 0 separately. Okay.
Okay.
So represent the following 4 numbers in BCD. That means 4, 15, 27, 103. So let's move to the next one. Right. So first of all, Now we are going to look at how to represent characters, numbers, symbols. Now is especially, let's say you type some character in the keyboard, how computer understand this, right? So there are many ways to, represent this, and people come up with different coding, and one of the extensively used one is called American Standard Code for Information Interchange. In short, we will say ASCII. So in ASCII, it uses 7 bits. Each of the character represent using 7 bits, right? So 7 bits means, sorry, um, it uses 7 bits to represent, and the number of characters you can represent is 120. So in ASCII, you had 128 characters using 7 bits. Okay, now let's go to the your textbook. Take your textbook, right? So I'm sharing the textbook. Go to the numbers. We are going to look at the ASCII representation. If you go to page numbers 102, you will see some table like this. And you see the first column is in decimal, then the ASCII characters given in the last column, that means first, second, third, fourth, fifth column. So you have to look at the first column and the fifth column, the values. If you go along this one, let's first of all look at, yes, how numbers are represented. So we have to go in fifth column. If you go along this fifth column, so you will see 0 here, right? So let me select this. I'm going to use a highlighter. So this is the first one. Yes, 0. That means decimal value it represents is 48. So likewise, if you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the numbers goes from 048, 048. That means decimal number 48 to 57. So the numbers 0 to 9 represent using ASCII with decimal numbers 48 to 57. Right. Likewise, let's go and look at capital letters. Okay, here capital letter starts with capital A. The decimal equivalent number is 65. Right. So start with 65. Likewise, B 66, C 67. So likewise, if you go alone, the C last one is 90. Likewise, if you check on the simple letters, simple A start with 97. And then that goes on to the last simple C, we have 122. So the values are 122. Okay, so let's go back to our note. Let me share it again. So here is our note. right? I have to fill from the beginning again. So this can be used to represent 128 characters, 128, and we need to use 7 bits for this, right? So the characters numbers 0 to 9, we represent using decimal numbers. The 0 represent with 48 and it goes up to 57. Then capital letters A starts with 65, 65 goes up to 90. Then we have simple A to Z, right? Simple A starts with 97 and goes up to 122. So this is in decimal values. What you need to remember when you convert something in given in characters into binary representation, we need to remember that each character represent using 7 bits. And these are the values given in decimal number. Although we have decimal number, we have to represent this in binary using 7 bits. That's what you need to remember. Okay, so having said that, let's start with the first example. So let's convert the word computer to a binary number using ASCII, right? Binary number using ASCII. So the first step is you have to look at each of the character. So that means C, right? O, M, P, U, T, E, R. So you have to represent each of these separately in binary. So first of all, let's start with the C. So what is the equivalent decimal value for character capital C, right? We know that capital A is 65, right? That we have discussed this earlier. B is 67, 66. That C means 67 there. So this should be 67. Now represent 67 using 7 bits. Now to do that, you can think about the positional values. So remember I told you you have 1, then you have 2, then you have 4, 3 bits, then 8, 4 bits, 16, 5 bits, 32, then we have 64. So that's how the numbers goes. So if you need 67, that means you need 64, then 0, we have 3, we need 0, here so 0, 0, 3, so you have to have 1, 1. So the value 67 in binary, capital C, can be represented in binary as 1, 0, 0, 0, 0, 1, 1. Right? So this is 79. So that means 64. That means we need 15, 0, this is 0. So when you say 15, 1, 1, 1 1, right? So that's how we will get 50. Right, 50. Then M, then M is 77. So you have to subtract 2 from the previous one. Yes. So that's why we have done the subtraction. So that is 80. So this is 80, which means you can add 1 to 79. So that means 64 and 16, right? So we have 1, 0, 1, 0, 0, 0, 0. Then we have U. So U is 85. You have to add 5 to this. So that means 1, 0, 1, right? Then 0, 1, 0, 1. Right? Then T is 84. You have to subtract 1 from this. 1, 0, 1, 0, 1, 0, 0. E. So that is 69. 69 means 64 plus 5. So that means 1, right? Then we have 0, 0, 0, 1, 0, 1. And finally R. Yes, it should be 82. That means 64, 16, 80, 0, 0, 1, 0. Right. So this is the representation. So the answer, final answer is you have to put everything together. So that means C 1, 0, 0, 0, 0, 1, 1. O 1, 0, 0, 1, 1, 1, 1. M 1, 0, 0, 1, 1, 0, 1. P 1, 0, 1, 0, 0, 0, 0. U 1, 0, 1, 0, 1, 0, 1. T 1, 0, 1, 0, 1, 0, 0. So this is how the word computer is represented inside the computer using ASCII.